In the absence of food, or if blood glucose concentration falls for any reason, insulin secretion is suppressed, and secretion of the insulin antagonist hormone glucagon from alpha cells of the pancreatic islets rises. The increased circulating level of glucagon has a number of effects. Glucagon stimulates release of free fatty acids and glycerol from fat cells. Furthermore, in peripheral tissues such as skeletal muscle, glucagon promotes the uptake and use of these free fatty acids as an energy source in preference to glucose. Glucagon inhibits glycolysis and promotes the metabolism of free fatty acids to drive the Krebs cycle in this tissue. Glucagon also promotes release of glucose from glycogen stores, reducing the tissue's dependence on circulating glucose. In the liver, in addition to this inhibitory effect on glycolysis, glucagon triggers upregulation of gluconeogenesis and also upregulates release of glucose into the bloodstream from liver glycogen stores. In effect, the increased glucagon levels have shunted glucose away from peripheral tissues and maintained the critical level of circulating glucose for use by the brain. When blood glucose levels rise after food ingestion, insulin secretion also rises, and the effects of glucagon are reversed. Throughout history, human populations have experienced periods of starvation. A metabolic switch in which glucagon plays a key role has evolved, which functions to protect the brain's glucose supply during periods of food deprivation. The main site of these effects is in the liver. If we focus in on the Krebs cycle, illustrated here in a little more detail than previously, we've already seen that glucagon promotes the formation of glucose from a Krebs cycle intermediary, specifically oxaloacetate. This gluconeogenesis replenishes glucose but depletes the level of this key intermediary in the Krebs cycle. Glucagon also promotes the mobilization of free fatty acids from adipocytes and the uptake of this species into the mitochondrion of hepatocytes, effectively promoting free fatty acid beta oxidation. As you will remember from biochemistry, this results in increased levels of acetyl coenzyme A, the substrate for the Krebs cycle. However, in this starved state, oxaloacetate levels are depleted and acetyl coenzyme A cannot enter the Krebs cycle. In starvation, this has a very useful effect. Acetyl coenzyme A is shunted towards the formation of ketone bodies. Ketone bodies are an efficient energy source capable of entering the Krebs cycle. The ketone bodies produced by the liver are extruded into the bloodstream. Crucially, unlike free fatty acids, ketones can cross the blood-brain barrier and can act as an energy source for the brain. Hence, blood glucose levels can be allowed to fall to an extent without compromising brain function. This is crucial as the only source of carbon for de novo production of glucose is amino acids, generated by muscle breakdown, reducing further the chance of survival. As we will see, unchecked activation of this metabolic starvation response is devastating in diabetic ketoacidosis.